Okay, so let's continue doing some problems. Remember, our steps are to separate, integrate, and isolate. So I think we're ready to do this far down. So what I want to do now is this problem. Let's say we had, I think this is example 6 now. So example 6 is that x times dy dx is equal to y, right? So we could separate now. We might do a little bit of algebra first and rewrite this as dy dx is equal to y over x. So we could pretend that's our algebraic phase. But now what do we need to do? We need to be able to get y to the left and everything with x to the right. So that's our separate phase. And so when we do that, to get y to the left, we have to divide by y. To get dx to the right, we need to multiply by it. So we have dx over x. All right, now this is sort of interesting. We're ready to integrate this. So you should know what both of those integrals are. Remember, we had said, let me put this over here, that the integral of dx over x, we were talking in terms of y, is really the same as the integral of 1 over x dx, but it's often written when you're working with differential equations as dx over x. So either way you write it, ln of absolute value of x is the answer, right? So here we go. We have ln of absolute value of y must equal ln of absolute value of x plus a constant, we'll call that C1. All right. Now, how do we isolate? We're ready to, we've integrated. Now we're ready to isolate for y. Okay, isolate y here. So we're going to exponentiate both sides, which means make it the exponent of e. And so then we're left with the absolute value of y is equal to, now this gets a little bit tricky here. We have e to the ln of absolute value of x plus c1. So we can rewrite that as e to the ln of absolute value of x, which will undo itself, times e to the c1. And remember that this is just another constant. So we can rewrite this whole thing as absolute value of y is equal to that constant c times e, and e raised to the ln of absolute value of x is just absolute value of x. Oops, let me get my pen back out, absolute value of x. Okay. Now this is a little tricky. We have to figure out what to do with all the plus and minus cases. So let's leave the absolute value on the left-hand side. Once again, the c can absorb the plus or minus value of y if I remove the absolute value signs. Okay, so remember, if y is greater than 0, y can equal c absolute value of x. But if y is less than 0, negative y could equal c times absolute value of x. So the constant can absorb the negative sign. So we can say that y is equal to c times absolute value of x. Right? Now let's do an initial value problem. Okay. Let's find the solution that passes through. Let's throw some negatives in there to make it interesting. Let's say that it passes through, let's say 1 comma negative 2, right? Well, let's substitute those in. Negative 2 is equal to c times absolute value of 1. Okay, so clearly negative 2 is equal to c, so y must equal negative 2 absolute value of x. That would be the solution that passes through 1, negative 2. Let's switch that around. Let's find the solution that passes through negative 1, 2. Okay, so if we have that, then we better say, okay, starting with going back to the general solution, we substitute in that 2 is equal to c times the absolute value of -1. So clearly absolute value of -1 is 1, so c is equal to +2 this time. So y is equal to, let me get this right, 2 times absolute value of x would be the solution to that. Okay, so there we have the possible solutions. If x is, yes, so there you see two special case solutions for that, or I should say initial value solution. You probably kind of heard me stumbling because as I was thinking on my feet, I had to realize, okay, I probably should do something with this. We're looking at x being positive, and so when x is greater than 0, absolute value of x is just equal to x. So I actually could say that this solution is -2x as long as we're in this region of the graph where x is positive, all right? And I could do a similar thing here. When x is less than 0, then the absolute value of x is equal to the negative of x. All right, so I could say the answer to this is y equals -2x once again. All right, so you can see we get the same solution. The line y equals -2x would be describing what's happening as it passes through things in either, this looks like that would be a fourth quadrant answer or initial value, and that would be a second quadrant initial value. And we would see that if we had first or third quadrants, we would end up with something more like y equals 2x without the negative sign. So that would be a better solution that can get rid of all of the absolute value signs and incorporate the initial values of this problem. Okay, so that was example 6. Let's move on to example 7, right? So we ended up with a y over x there, yes, okay. So example 7, I'm sure I wasn't doing the same thing twice. Example 7, we'll have -y dy dx is equal to x. We won't bother with the initial value solution this time. We'll just get the general solution. So to separate this, all we need to do is multiply both sides by dx. So -y dy is equal to x dx. Okay, so why don't you see if you can integrate both sides and then start the video again. Okay, so you have a negative there. When you integrate, you should get y squared over 2 on this side equals x squared over 2 plus, we'll call it a c1, right? Now we could actually make our lives easier and put c1 over 2 as well. Since it's an unknown constant, it might as well be an unknown divided by 2. So now everything's divided by 2. And so we can see this would be -y squared is equal to x squared plus the constant that we were looking for. All right, we'll call that C1 still. All right, well, let's write this in a form. This time we're not actually going to isolate the y. I'm going to actually rewrite this a different way. I'm going to rewrite this as -C1 is equal to x squared plus y squared. And what if -C1 happened to equal something like, oh, let's call it r squared? Oh, this would be the equation of a circle where x squared plus y squared is equal to r squared. All right, so when we look at this differential equation, it's not so obvious, but the solution to it is a circle. So the general solution is a circle, and then if we gave an initial value that it had to go through, that would determine what the radius of the circle is, which would be the specific solution. Now we could have done this where we did isolate and solve for y. You would end up with y squared is equal to c1 minus x squared, actually -c1. But if we replace C1 with negative C1 with R squared. We could say that Y squared is equal to R squared minus X squared. So Y is plus or minus the square root of R squared minus X squared, where the positive root gives you the top of a circle and the negative root gives you the bottom of the circle. But we can use the implicit form and get the whole circle. So sometimes it's better not to solve for Y when it gives us something with which we're familiar.